We good to go, Matthias?
Yes, you can start.
Okay, thank you. Okay, so good afternoon, everybody, and welcome to this session on network and flow management. My name is Radosav Jovanovic, and I'm associate professor at University of Belgrade, and I'll be chairing this session. We have three very interesting papers today, and three presenters are ready here with us. So it will be Daniel Lubig, Ramon Dalmau, and Tanja Bolic in this order. So the first paper will be, before I start, just on top of those three papers, after that, after the third one, we will have one of the poster teasers. So please stay after the last presentation is done. So it's only a couple more minutes to see this interesting poster teaser. We will start with Daniel Lubig and his presentation, which is titled Modeling the European Air Transportation Network Considering Inter-Airport Coordination. I will just briefly introduce Daniel before switching over to his presentation. So Daniel Lubig is currently pursuing the PhD degree at the Institute of Logistics and Aviation at Technical University of Dresden. His research interests include airport network operations, demand capacity balancing due to management of long-range flights, and the improvement of terminal operations using new technologies. So Daniel, over to you. The floor is yours.
So I hope you can hear me well and you can see my screen. Yeah, I see the thumb up, so I will start. Thank you, Radosav, for the kind introduction, and hello to everyone behind the screen. To my presentation, achieved by our research team located at the University of Technology in Dresden, and in strong collaboration with our fantastic partners from Eurocontrol sitting in Belgium and France. And the presentation has the title, Radosav also said this, Modeling the European Air Transportation Network Considering Inter-Airport Coordination. I will start with a brief introduction into the topic, followed by our methodology to model the European Air Transportation Network. Point 3 addresses the methodology to determining flight connections from full-service network carriers. And afterwards, I will show you the simulation setup and the results. And last but not least, a short conclusion and the outlook for further research. Eurocontrol in the recent years observed two constant trends, and I think everyone from you participated in the aviation sector also recognizes that we had before 2020 a consistent growth in number of carried passengers and flight numbers. And this is paired with also an increase in delay. And these delay reached some unsatisfying levels, especially in summer 2018 and 2019, which indicates that the capacity limits in the air transportation network are somehow reached. It also gets a little bit more worse when we have to look into some forecasts. And here the challenges of growth published by Eurocontrol, they predict more traffic flights, 30% more traffic in 2040 compared to 2017, and a capacity gap of 1.5 million flights. I have to state that these are values published before the impact from COVID-19. And if you attended yesterday at the opening ceremony or the opening event and listened to the speak from Eamon Brennan, then you know that this Corona crisis has a huge impact on the aviation sector, and it will need time to recover. But as a positive-minded aviation researcher in a positive aviation community, we are thinking, okay, these or the aviation will recover from this, and the growth will come, but we need maybe to shift the 2040 a little bit further away into the future. But nevertheless, there are some documents, some strategic documents in Europe, the Flight Path 2050 and the ATM Master Plan. And these documents, they define some quality goals. And these are really hard to reach, especially if we have to consider the predicted growth and the actual delay in 2018 and 2019. This all comes together, and we have to conclude, okay, somehow we need some capacity increases. And with our study, we want to answer the questions how the improvement in local capacity affect the overall performance of hub airports, and how does the local capacity increase affect the connection rate of local full service network carrier. And as a little bonus, we want to see, are there some network effects? So which means are some other airports or full service network carriers are also improved, which are not directly threatened by some capacity improvements. It's important to note that the research does not answer the question of how the capacity increase is achieved. We just assume, okay, the airports are somehow able to do this. There's a small discussion about this topic within the paper, but I don't want to address this here because of the time limitation. Let's start with our development from the air transportation network model, and therefore Eurocontrol provided us a data set, and the data set contains planned and actual information of reported flights during the busy summer months from July to September 2019 in the busy summer period. And the first question from us was, okay, we want to model a network, which airport should be included into the network? And of course, you start with the most important ones, the busiest airports. And that's why we decided, okay, let us rank the airports by number of movements. And you can see the results on the left corner here. We start with airport 1, the busiest in Europe. And then we ordered the airports in a descending order to airport 1834, which is the airport with the lowest number of tracked flights. And if you see the curve here, then this should remind you to the Gini coefficient. And the Gini coefficient is a measure to which reveals unequity. And unequity is also the case here in Europe. You can see that 38 airports in Europe handle more than 50% of the traffic in Europe. So if we have to make the final decision, okay, how many airports we should cover with our network, then there's a trade-off between two factors. One factor, we want as much airports as possible because more airports means more traffic is covered by the network. On the other side, there is the computational effort. So every more airport needs computational processing time, and this makes our simulation slower. To address both of these factors, we decided, okay, let us take 212 airports. These airports are handled more than 90% more than 90% of the movements. On the right side, you can see where are the airports located. And since you are all sitting behind screens distributed in all of Europe, I am pretty sure you find your regional hub airport on this map, or the airport which brings you to your favorite summer vacation destination. So after defining the scope of the network, we can have a further look into the model logic, and we decided to model it as a node edge network, where the node is represented by airports, and the airports are characterized by the number of available runways. These runways serves as server for takeoff and landing operations, and every landing and every takeoff needs some time. And the process time for the runway procedure depends on the runway occupancy time. This is the time the aircraft needs, or that the aircraft has physical contact to the runway, and the wake turbulence separation. This guarantees safe operations in the vicinity of the airport. This processing time also limits the runway capacity because only one aircraft is allowed to use the runway at the same time. The runways are also implemented as a queue system, which means if an aircraft is using a runway and another aircraft wants to use it as well, the aircraft has to wait until the runway or the facility is empty and it's their turn to start their procedure. It's important to note here that no local operation procedures are considered. You can imagine 212 airports. Every airport has some own specific procedures. These are not considered here. So let's have a look at our edges. So the connections between the nodes, these are served by flights. Flights is not precise enough. I have to say these are flight circles. And these flight circles consist of 4 phases. These are shown here in orange. So it's the outbound roll time, which means it's the taxi out time. 2 is the flight by itself. 3, the inbound roll time, which is the taxi in time. And 4 is the ground time, which includes the turnaround. And each of these phases is delimited by a time stamp. And these are the off-block time, the time of departure, the time of arrival, and the in-block time. And both or all 4 of these times, they are available in a scheduled and in an actual information. And now it's the case that that aircrafts are used for more rotations during an operation day. And on the bottom right side, you can see an example for this. This is an aircraft with the registration DAIQH. And you can see on this planned day, on flight plan, which is used within the simulation, 7 flight circles are planned for these aircraft, starting at Frankfurt to Toulouse. And every row represents one of these flight cycles. So this row is only fulfilled when all these steps are executed. So we all know our 4 phases for a flight. And now the question is, how long does these phases take? And let's start with the flight time. And within the data set, there are the actual flight times reported. And I've shown you, or I will show you the flight times from London Heathrow to Frankfurt, which was flown with a Air 320 Neo aircraft, because it's important to consider the aircraft type. As you can imagine, there's different aircraft types have different speeds, and this also this affects the flight time significantly. You can see the blue bars representing the flight times, and the red curve is the normal distribution calculated based on the blue bars. And you see the red curve runs a little bit flat because a lot of outliers are considered here, some especially high flight times over 1 hour and 15 minutes. These are flight times which occurs maybe because of a lot of holding procedures or bad weather at London, and the aircrafts need to stay in the air somehow, or however, these are not the usual case of flight time. We want some unimpeded flight times, because our simulation is able to generate additional waiting time by itself. Remember, our runways are queuing systems. So, and if the runway is occupied, then the aircraft has to wait, and this is also represented by these high flight times. So that's why we decided, okay, we exclude these outliers, and we only consider flight times which are located within the 2 sigma area. And you can see the green line is the new curve, which is formed using only these values. And this has a way better fitting curve, is a way better fitting curve than the red one. For the turnaround time, we used a basic assumption based on the wake turbulence category from the used aircraft. And for each category, reference aircraft is defined. For example, for the medium flights or the medium aircrafts, these are the A320neo. And then Airbus, as a manufacturer, they publish an turnaround time, and we took this as an assumption, or as an assumption basis. So the both missing flight phases are the taxi out time. This is similar to the flight times based on the actual taxi out times reported in the data set. And you can see here on the right side 2 examples, one for Frankfurt and one for London Heathrow, and which shows the mean and standard deviation based on the airborne traffic volume. So, for example, here for this bar, this includes all aircraft which started the taxiing procedure when 6 aircraft are simultaneously, taxiing on the apron. The gray bar is the mean time. The black bar is the standard deviation, and the red bar shows you how often this traffic volume occurs. And you can see for both airports, so the time where 0 aircraft are on the apron is really high. This is a reason due to the night flight bans on both airports. And if you compare these 2 pictures, you see a major difference. The top right figure shows somehow an airport which is resistant against congestion effects on apron. So even for high apron traffic volumes, the mean taxi out time remains stable. This is, I would say, the more uncommon case. The more common case for taxi out times is shown on the bottom right. For example, here London Heathrow. And here we have also stable taxi out times for low traffic volumes. But after a transition point for London Heathrow, this is 7 aircraft. Every additional aircraft leads to more taxi out time, and this results from congestion effects. So the aircraft are interacting, need to brake or to wait, for example, and that's why the taxi out times are increasing. Similar to our flight times, we just want unimpeded taxi out times. That's why we decided, okay, let us simply take the taxi out times when 5 or less or 5 or fewer aircraft are taxiing on the airport. And last but not least, the taxi in time. This is a little bit easier because the reported values, they differ between the network airports, but remain the same for one airport, which means for Frankfurt, these are always 8 minutes, and for Dresden, these are always 4 minutes. And we just took this constant value as an assumption for the taxi in time. So we now have our simulation. We have our process times, and now we can think about how to assess the full service network carrier. And here we wanted to grab the centerpiece of this airline model. And this is the connection from an origin airport with the destination airport via the corresponding full service network carrier hub airport. And I think you all know what an OND or an origin and destination connection looks like, but I wanted that we all have the same picture in mind. So here's our definition. We're starting at the origin airport. We're using the leg 1 flight. We arrive at the hub, need to transfer to our leg 2 flight, which brings us to the destination. To define our planned connections, we used a 3-step approach, and we started with a times-based assumption, which means we are looking which leg 1 flights are connected to the leg 2 flights. That includes a backward calculation, I would say. And this is shown on this picture here. We have a leg 2 flight from Frankfurt to Stockholm. And now we are showing backwards how many flights arrive at Frankfurt in a given time period. And the time period is delimited between 3 hours before the standard time of time of departure from the leg 2 flights. So here the idea, or we argue, it's of course possible that some connections, or you have to wait, for example, 8 hours at an airport, but these are not the planned connections from the airline. So this sometimes occurs, but this is more, the unusual case. And then at every airport, you have a minimum connecting time. So this is the time which guarantees you to reach your leg 2 flight at the airport, which guarantees you as a person and your luggage as well to connect these flights. For this case here, for this example case, this means flights from all these points, from the green points, are possible connected flights. Only consider the time-based assumption. And then you can see, okay, we have a spatial problem, because it could be possible that 2 nearly close connected aircrafts could form a valid OND. But this is not suitable, because I think these close distances are covered by high-speed trains, long-distance buses, or another transport mode. And that's why we defined an excluded area. And the excluded area is formed through 4 borders. There's 2 distance borders and 2 angle borders. The angle occurs here, theta, between north, the hub airport, and the destination airport. And with some threshold values from 600 kilometers and 20 degrees, this red area occurs, and all leg 1 flights from this airport are excluded or are marked as non-valid feeder flights for this specific second leg flight. This logic works really well for our inner European ONDs, but somehow these are not suitable for long-range ONDs. And you can see this here. So this is the excluded area, which occurs when we look Miami as an origin, Frankfurt as a hub, and New York as a destination. And here you can see, okay, if we only consider our first approach, this would be a good OND, but we don't want to want this behavior, and that's why we introduced a detour factor, and the detour factor provides, or this neglected this definition of 2 long-range ONDs close each other in the same region of the world. Okay, we have our simulation, then we need to start the machine. I talked about the flight plan, so I skipped this part. We defined two scenarios. The baseline scenario doesn't consider any capacity improvement. Scenario 1 and 2, they are considering the capacity improvement at Frankfurt and 2 in London Heathrow. And then we are checking 5 key performance indicators. So for the airport performance, inbound delay, outbound delay, additional taxi out time, and the ASMA additional time. And for the full service network carrier, the connection rate, which is the rate between the fulfilled flight connections and the planned flight connections. And let us have a look on the results. So this is the more, I would say, boring results. So nothing happened here. And we can see Frankfurt is not a congested airport. So capacity improvement doesn't have any effects, doesn't improve the full service network carrier connection rate. And all in all, this is the typical case of improving a system which is not congested. It doesn't have an effect. More interesting are the results for London Heathrow, because here we have the congestion effect. And if we improve the capacity, you can see, okay, our key performance indicator, they improve as well. And the values here are pretty high, I would say. And also for British Airways, the connection rate of British Airways, we can see if we increase the capacity, more flight connections can be achieved by the passengers. Other full service network carrier performances are also slightly improved. It's hard to see here, but for example, KLM, they also can increase their connection rate because of their flights which are flying to London. They are improved, and these improvements, they spread a little bit into the network of KLM. In both cases, so for the airport and for the capacity, for the airport and for the airlines, we can see a saturation effect, so which means a higher capacity enhancement doesn't have the same effect, especially when you considering or when you compare this to the lower capacity enhancement. So I will leave you with a short conclusion to answer the research questions. At first, the capacity improvement leads to airport performance increase if the airport is congested. That's important to state. The same occurs when you are looking at the local full service network carrier, and the performance of full service network carrier using the capacity improved airport as spoke airport are also improved slightly. But I would say the network effects are not that significant or not that high as expected. So the small outlook, this is a basis to exclude or to extend. This is the right word, to extend the methodology and to include the airline rules, for example, to add a delay cost analysis, or just to improve the European airport network model, because some assumptions can always be replaced or can be sharpened. So that's all. Thanks for your attention, and I'm now ready for your questions, marks, hints.
Okay, so thank you, Daniel, for the interesting and lively presentation. I see that we already have one question in the Q&A panel. It's Margarita Bagamanova, who's asking, Daniel, what is the source of your flight data?
The source is Eurocontrol, I would say. So they provided to us this data set. What's the original source? I can't say in detail. So there we need the help from the Eurocontrol part, or the Eurocontrol guys which worked here in the paper. But yeah, I think this is the answer I can give to this question.
Okay, at the moment I don't see any more questions, but hopefully some will come in. So while we wait, I have a couple of questions which were ready as a backup option. One question is about these minimum connecting times, and then you described the way you were trying to take this into account in this 3-step procedure. So would you see an option to actually improve this by somehow validating against, well, some other source of data which is more connected to the real world, to put it that way?
Yeah, here we run into a problem that minimum connecting time depends also for airports. In Frankfurt, for example, if you need to change the terminal, this takes more time than for example, you have to reach another inner European flight. So for some airports, there are different minimum connecting times. It's possible to rethink about these times, but then we have the problem. We have 212 airports. So, and if you do this for every airport, this is a bunch of work, which is maybe not sensible to do. But it could be useful, especially for the airports. So London Heathrow is the most congested airport. Here it would be worth to look further into the topic and maybe to use these more realistic values obtained or measured in the real world.
Mm-hmm. Okay, so in the meantime, we have one more question from Margarita. It says, what simulation software did you use?
I used Python, and there are some tools. Or the major part tool for the simulation called SimPy.
Mm-hmm.
Yeah.
Okay. And one more from Margarita. So what was the main objective of the model? Okay.
I would say the main objective is to receive my PhD. So we are using this model to just investigate how capacity affects the network. So usually today you are saying, okay, the airport is congested, we need a new runway, but no one thinks about the network. So what's this meanings what does this mean for the network? So are there some profiteers on another place in Europe? Some other airports could be improved as well. And this is something we want to show. It's called benefit propagation. You all know maybe the term delay propagation. So the delay spreads into the whole network, and we think this could be the same for capacity improvement, so for benefits.
Okay, so thank you, Daniel. I don't see any more questions at the moment in the Q&A. If you happen to get any later, you can reply in written. So thank you once again, and we are moving on to the next presentation, which will be given by Ramon Dalmau Codina, and it's titled, "Are all the requested ATFM regulations actually indispensable?" So just a quick introduction of Ramon before I hand over to him. Just a second. So Ramon is a data scientist in the network research unit of Eurocontrol, where he is currently working on algorithms to improve trajectory predictions. He is an aeronautical engineer from the UPC Barcelona and holds a master in computational and applied mathematics from the Autonomous University of Barcelona. In 2019, he obtained a PhD in aerospace science and technology from the UPC, and his main research areas of interest include optimal control and nonlinear optimization, as well as machine learning, in particular reinforcement learning, as you will see in the coming presentation. So Ramon, the floor is yours.
Thank you very much for the introduction. The paper that I'm going to present originated from a question, which then we decided to keep as the title, because it summarizes very well our objective. To check whether all the requested air traffic flow management regulations are actually indispensable, or maybe some of them are not effective. But before starting, I would like to acknowledge all the members of the team. So Leila, Camille, Darren, and also Benjamin, because each one of them has played a very important role in this project. This is the outline of the presentation. First, I am going to explain the problem, and then we are going to define the problem in mathematical terms. I will also explain the optimization algorithm, but briefly, and I am going to show its performance with an illustrative example. As usual, we are going to finish this presentation with some conclusions and future work. So in Europe, the most common air traffic flow management measure used by the network manager to solve demand and capacity balance problems consists of imposing air traffic flow management regulations. In the following image, you can see a traffic volume which is associated with a sector in the southeast of Spain. And this figure shows the demand, which are the vertical lines, bars, as well as the capacity, which is the horizontal line along the day. In this particular scenario, you can see that the traffic volume was open in the morning and also at the end of the day. And a regulation was put in place at the very end of the day because the demand was above the capacity. Then the computer-assisted slot allocation system assigned ground delays to the flights entering in this time period, the time period of the regulation, in a more or less first come, first served basis with some exceptions in order to smooth the demand. So as a result, the overloads were solved, but at the cost of some ATFM delay. When only one regulation is in place in the network, the problem is very easy. But during busy days, especially during summer, many regulations are requested by the flow managers. And these flow managers request the regulations independently. It's the network manager who has the role of coordinating the set of regulations that are in the network. But a flight subject to several regulations simultaneously is assigned with the most penalizing or the highest delay. So the highest delay of all regulations that are affecting the flight. And then it's pushed into the other regulations with this delay. This means that regulations with flights in common influence each other. In this figure, for instance, we see a regulation B that interacts with our first regulation, the regulation A. And they have some flights in common, as you can see. But maybe many of the flights have B as the most penalizing regulations. And this means that A is not effective and that maybe we can safely remove this regulation because they were proposed by different flow managers without coordination. But the new solution must reduce the total ATFM delay. This is our objective. But we cannot create overloads elsewhere in the network by removing or canceling regulations. And these are our constraints. So this is a binary combinatorial optimization problem. Because we must decide if we keep or remove each one of the regulations that are proposed. With two regulations, there exist only 4 possibilities. So it's an easy problem. But in practice, this cannot be solved by hand because with only 25 regulations, for instance, and this is quite small, there exist 2 at the power of 25 possible combinations, assuming that each regulation can be either cancelled or active. If then we play with the parameters of the regulation, the combinatorial explodes. In mathematical terms, we want to find the best binary vector where each element of this vector corresponds to one of the regulations that are proposed by the flow managers, such that the total ATFM delay is minimized, where the delay created by each one of the regulations depends on which regulations are active, because regulations interact. And at the same time, we must not create overloads by canceling regulations. So we must ensure that if we remove a regulation, the demand is still below its rate or capacity during the whole period. For instance, in this figure, we removed the regulation, which has a capacity of 52, and we created some overloads. So you can check how much the bars are above this 52. And if you sum all the values, the overloads are 56. And we must keep this 56 to 0. And this is one of the constraints. The problem is that we cannot solve this optimization problem with mixed integer programming because the functions f, which is the delay created by each regulation, as well d, which is the demand in the time period of the regulation, are very nonlinear functions of our binary solution vector. We cannot model this with linear equations. Furthermore, if we consider the constraints as hard constraints, even one single overload somewhere in the network will invalidate our solution. But maybe the solution was very good in terms of delay. So we should consider these constraints as soft constraints, not hard constraints. We addressed this binary combinatorial optimization problem as a weighted constraints satisfaction problem, in which we just want to minimize the violations of a set of constraints. In order to accomplish that, we just transform the objective, the minimization of the total ATFM delay, into a set of constraints, which state that the delay created by each regulation must be negative. We all know that the delay cannot be negative, and this is equivalent to say minimize the total ATFM delay. So now we have a set of constraints composed by 2 subsets, the set of delay constraints and the set of overload constraints, and we just want to minimize the constraint violations. So we effectively transform an optimization problem into a weighted constraint satisfaction problem. Again, we want to find the best binary solution vector where each element of the solution vector corresponds to one regulation, indicating whether the regulation is cancelled, 0, or active, 1, such that a given penalty function is minimized. And this penalty function is a weighted sum of constraint violations, where the weight associated to each constraint indicates the importance of the constraint in the problem, and is a positive value, of course. And the set of constraints include the delay constraints and the overload constraints. And each regulation in the set of regulations that we want to optimize is associated with two constraints. The delay constraint that states that the delay of this regulation must be negative, and we want to penalize those violations, and that we cannot exceed the capacity. So the sum of overloads must be also negative. But now we have new questions. How to set the weight that is associated to each constraint? Because constraints with small weights will tend to be ignored by the algorithm. But too much emphasis will be placed on solving constraints with very large weights. Furthermore, what is more important, delays or overloads? We'll know that overloads, but how much? And are all the regulations equally important? Since we cannot answer these questions, we dynamically adjust the weights during the search, depending on the constraint violations. We'll see this later. So we have our original penalty function, which is the weighted constraint of violations, and which weights are fixed. They are fixed, we cannot touch them. And we have another function that is the evaluation function, that is the function that we use during the search. Okay, we are trying to optimize this evaluation function, and is identical to the penalty function, and the only difference is that the weights are adapted. We can change these weights. We dynamically adjust these weights during the search. And these weights are positive, of course, and cannot exceed the original penalties weights. But how to minimize this evaluation function? And secondly, and more important, how to dynamically adjust the weights during the search. For the first question, actually any optimization method could work. So you could use simulated annealing, genetic algorithms. In this case, we selected Tabu Search because we tried many algorithms, and this one was providing very good performance. For the second questions, we are updating the weights based on the current violations. So if we see a constraint that is highly violated, we increase the weight. Instead, if we see a constraint that is not violated a lot, then we decrease the weight, giving more flexibility to the optimization solver. You can find more details about the algorithm that we developed in the paper, but in short, we are repeating a Tabu Search round, which is a standard algorithm, in order to update the current solution with Tabu Search, in order to minimize the evaluation function. Remember that the evaluation function is identical to the penalty function, but with dynamic weights. Then, when we find a local optimum, we check if the current local optimum is better than the incumbent, where the incumbent is the best solution found so far during the search, in terms of penalty function, okay? And then we update the weights. Again, the Tabu Search and the penalty weight update routines are explained in the paper. To simulate the cancellation and activation of regulations, we use the Network Manager Validation Platform, which fully replicates the real network management operational system, including CASA. So our algorithm is running in Python, and it's getting the data from the NMB2B service, and also calling the real CASA. So we are really calling the CASA and getting the real data. In order to validate the algorithm, we replayed a past day, because nowadays the traffic levels are very low and there are no regulations. We replayed a very busy day, the 27th of June of 2019, in real time, starting at 7:40 a.m., when 120 regulations were active in the network, generating 43,000 minutes of delay. But during the optimization, we only considered air traffic control capacity regulations, and we reduced the scope to Spain, France, Belgium, Germany, Luxembourg, and the Netherlands airspace, in which 21 regulations were generating 5,300 minutes of delay. This means that we have almost 2 million of possible combinations. And running each one of these simulations with the real CASA and getting the real data from the B2B service takes between 3 and 7 seconds. And of course, we cannot wait forever. So we limited the number of solutions to 100, which is approximately 5 minutes. And this means that the algorithm had to converge by exploring less than 0.01% of the total search space, which was very challenging. We optimized a local region, so only a subset of the network, but we must ensure that the effect of canceling the regulations proposed by the solver is positive network-wide. And this is why the local optimization was then followed by a network impact assessment. And now I am going to show the results. The slide shows the map. So you can see in the left, the region that we were optimizing with 21 regulations. The optimizer proposed to cancel 7 of these 21 regulations, and you can see the map in the right now. So we have now 13 regulations. This table shows the result of the local optimization. So the delay difference for the 21 regulations that were subject to optimization. So in the subset of the network. And we can observe in the last column, in the last row, that the net effect was a reduction of 1,380 minutes of delay in this subregion of the network. Each row of this table corresponds to a different regulation. And the last column shows the delay difference before cancellation and after cancellation. So negative numbers are good, and positive numbers are bad because we are increasing the delay. And in red, we highlight the regulations that were canceled in the simulation. We can observe that, of course, the regulations that were canceled show a very big reduction of delay. For instance, in the first one, we reduced the delay by almost 100 minutes of delay. For the regulations that were not canceled, in black, we can see that some of them had no effect, so the difference is 0. And in some of them, we slightly increased the delay, with the maximum increase being 130 minutes of delay. It should be noted that some regulations that were canceled, they still had some delay after cancellation. And this is due to the fact that some aircraft were already airborne. And if you cancel the regulation, you don't have effect on these aircraft that are already airborne. But this table shows the result just for the 21 regulations subject to optimization. What about the other 19 regulations active in the network at that time, but not optimized? And what about the traffic volumes that were not monitored during the optimization process, but that they were active? This slide shows the results of the network impact assessment. In the left, we see the delay difference for the 120 regulations active in the network. Again, we can see that some of them decrease the delay and some of them increase the delay. But the net effect, network-wide, was a reduction of 2,200 minutes of delay, which represents a 5% of the total delay generated by the regulations that were active at that time. Then the table in the right shows the difference in alerts due to overloads for all the traffic volumes that were monitored in the network. An alert happens when the overload, when the demand exceeds the capacity in a given monitoring window of 1 hour. So this is considered an alert. And we can observe that in general, the changes were really small, being the distribution very narrow between -2 and +2. So we have some TVs in which we decreased the number of alerts. We have some TVs in which we increased, but the maximum increase was just 2. And the global effect, network-wide, was a reduction of the total number of alerts of -3. So conclusions and future work. Are all the requested ATFM regulations actually indispensable? Well, this is a very difficult problem due to the complexity of the network and cannot be solved by hand. In this paper, we proposed Tabu search with strategic oscillations to identify which regulations could be safely cancelled while minimizing the total ATFM delay of the network. But other algorithms may also perform good at solving this problem. We also tried adaptive large neighborhood search, harmony search, which is similar to genetic algorithms, branch and bound, but also simulated annealing could work. In fact, we tried many of them, and we plan to show the results in future publications. The 16th of November, so less than 1 month ago, we performed a validation exercise at the Network Manager Operations Center in Brussels, and we executed 8 runs in a similar scenario with 2 different controllers. And we received very good feedback. So they were really happy about this tool. And now we are working to extend this algorithm to not only propose to cancel regulations, but also to create new regulations not existing in the system, and or to modify the parameters of the existing regulations, like the rate or the start time and end times, etc. And for this, we are using multi-agent reinforcement learning, but it's still work in progress. This figure just shows the operational exercise at the Network Manager Operations Center last month. In the left, you can see the CFMU tactical or TAC, and in the right, the HMI of our algorithm running in the NMOC. And thank you very much for your attention.
Thank you, Ramon. Very nice and clear presentation and a very nice paper, which I warmly recommend to everybody to read. I did so, and you already got quite a few of questions in the Q&A chat. So we will go by this upvoting method. So the first one was asked by René Verbeek. It says, are the changes in regulations fair, or are some sectors getting more of the negative effects on average?
Well, this is a very good question. Because even if we show that network-wide the delay reduces, it's true that some FMPs increase the delay in some ANSPs, which we observe an increase of delay, which maybe they wouldn't accept, even if the global delay is reduced. And in fact, when we were doing these exercises in the Network Manager Operations Center last month, the controllers in some times were rejecting our proposal for cancellations, because they say that the ANSPs would not accept such increase of delay, even if the global delay of the network was reduced, because at the end, this delay is attributed to them. But this is more a political issue, because maybe the network manager could assume this delay at the end. So, but this is not in our hands. We just wanted to prove that maybe some of the regulations could be removed without creating problems. But yeah, the delay attribution would be a limiting factor of our algorithm.
Okay, the next one is from Nikolai Ivanov. Says, great work as usual. Question, did you assume that all the regulations were known from the start, or you dynamically include them when they are activated during the day of operations?
Well, we assume, well, in fact, the algorithm runs by only trying to cancel or activate the regulations that are present at the moment of starting the optimization process. The optimization process takes around 5 minutes. And then, of course, you can run again the optimizer with new regulations if they have appeared. This is not an issue, but it's true that you need to run the algorithm in the background. And another important question here is that we only analyzed a static picture. So given this static picture, what if we remove some of the regulations? But removing these regulations will have an impact later during the day. So we should also analyze this.
Okay, thank you. Let's go further. So Soner has asked a number of questions here in this one block. So can you ensure that TS give a global optimum for this problem, or just a better than previous one or feasible one?
We cannot ensure that this is the global optimum. At the end is a meta-heuristic. As you have seen, there are plenty of combinations with 21 regulations, 2 millions. And exploring one single solution takes between 3 and 7 seconds. So we must limit the number of solutions that we explore because the network is very dynamic and we were running in real time. So we were not stopping the clock. So we were letting the clock run. So traffic was changing. The picture of the network was changing and we could not wait more than 5 minutes. This is why we limited the number of solutions. And at the end, we just get the best solution found up to that point. But we cannot ensure this is the global optimum. It would be nice to stop the clock and let the algorithm run, maybe during hours, maybe during one day, to see the gap between the local optimum that is found after 5 minutes with the global optimum or pseudo global optimums, because we can never ensure that this is the global optimum.
Okay, so I assume that you answered a number of these other related questions of Soner concerning at which iteration you reach the global optimum and what is the model performance in terms of solution periods. I think you mentioned this one that it runs very quickly, so something like 5 minutes, you said so, something like that.
Well, yeah, at the end, the execution time is a parameter. No? The more you wait, the more chances you have to get a better solution, of course. But the more the network will change. So maybe the solution that you get when you apply it is no longer valid. It doesn't provide you the result that you were expecting. So it's a trade-off between high quality solutions and waiting for them.
Okay, one more just right from Sebastian Wagnick. Ramon, does the algorithm scale to full ECAC? Is it parallelizable, for example, using cloud infra?
Yeah, first of all, now we have a limitation, is that we are executing CASA via B2B service, and this takes time. But the closer we are to the real CASA, to the real system, the faster it will be. So now our limitation is just the execution time of each single solution. Provided that we can run a CASA very fast, let's say in milliseconds or even 1 second, then maybe we could target to scale to the whole network. But again, in this validation exercise, we tried one of the worst days in the period of 2019. So probably in normal days, you don't have more than 60 or 70 regulations at the same time. Because remember that this is at the beginning of the day. We were running probably, most of them were pre-tactical regulations. But if we cancel these pre-tactical regulations, yeah, it will be much better.
Yeah, and then one more from René, which relates to his previous question and that one of Nicola. So are the solutions stable? Will an additional dynamic regulation result in a completely different solution? Well, who knows, but you can try and answer.
Well, it's true that since it's a meta-heuristic and it has some random component, every time you run it, you may get different solutions. And even more because we are only considering 100 solutions, iterations. So we don't let the algorithm to explore a lot. This is why every time you run it, you may get a different solution. Yeah.
Okay, and two more, and then we have to move on to the third presentation. So first from Adriana Andreeva Mori, a quick question on the definition of ATFM delay. Is this any delay, regardless of it being ground delay, controlled en route delay, or delay due to vectoring? Yeah,
it's all ATFM delay, but in this case, we were only considering regulations caused by ATC capacity issues, because there are regulations that you cannot cancel, like ATC staffing, no, or weather issues. We were focusing only on ATC capacity issues because we knew that are the ones that FMPs could negotiate.
Okay, so I now see that Milan has raised his hand and we have one more question in the Q&A, so I suggest we slightly break this slot. First, the one from Mustafa Özdemir. Thank you for the presentation. You said you cannot utilize mixed integer programming. Was the reason your objective function is nonlinear? Did you try to linearize if it is not linear? It's non-linear.
I didn't try to linearize, but I must say that CASA, the CASA system, because at the end, the delays depends on the rules of CASA as well as the demand. And the CASA system is very complex. I don't know if it's possible even to linearize the CASA behavior. No, it has a lot of exceptions, a lot of rules. It's super unpredictable in this sense.
Okay, and can we now try, please, to let Milan put his questions and unmute him? So Milan Janic, the conference director, can you do this? nothing is happening. I'm not sure. Okay, Milan, I think we can hear you now. Go ahead.
Can you hear me?
Yes.
The simple, presentation, in my opinion, has been very interesting and very challenging in the computational terms. But what actually about regulation is? What is that about? That's first question. Second question is, who is going to physically do that in terms of coming closer to optimization you are talking about? Of course, that optimum will never be achieved because of many other things. Who is going to do that, and is there any need for such many regulations you are talking about? Is there any plan at the beginning of the day about the performances, how the system is going to perform, and who is going to be given the slots and these kind of things? How have you considered that?
Well, we were only considering ATFM regulations, so not cherry pickings, because they are more short-term measures, only ATFM regulations. All the regulations that were at that time in the system, since we were in the morning, most of them were pre-tactical. So regulations that were put in place probably the day before in the night. But as I said, FMPs of the different ISPs do not coordinate. So it's the network manager who is coordinating. But so at the moment, they don't have any automated tool to check if a regulation is protecting another. So this was the idea of the project, to automate this process, to help the operator to see if some of the regulations could be safely removed. But at the end, it's up to the operator to decide if the solution is good and to start the negotiation with the FMPs, because at the end, the FMPs are the responsibles of canceling or activating a regulation. So at the end, this is a long process. From the moment that you get the solution from the solver to the moment that the solution materializes, it may take a lot of time because you need to coordinate with all the FMPs that are involved in this problem. But yeah, we need the human in the loop. This is not just an automated system that is running in the background and canceling regulations automatically.
How do you think that is going to be realistic, what you have been talking about?
Well, we performed some validation exercises last month, and they were very happy about this tool. They think it's very useful. And yeah, in fact, next week, we have a meeting to decide the next steps for this project. Yeah.
Okay, thanks. Thanks.
Thank you to you.
Oh, sorry, I'm muted. Thank you, Ramon, very much for this presentation and for all the answers to numerous questions. So thanks once again. And we are now moving with some delay to the third presentation in this session, which is titled Capacity Sharing within Virtual Center, and will be given by Tanja Bolic. So just a quick introduction of Tanja. Tanja is a senior research fellow at University of Westminster, working on air traffic management research. Her expertise covers a broad spectrum: ATM operations, performance, network management, automation and human factors, economics, meteorological information provision, crisis management, airport design, endless list, diffusion of innovation and logistics. And Tanja is a vice chair of the SESAR Joint Undertaking Scientific Committee. Okay, Tanja, so gladly over to you.
Thank you. So okay, let's see, window, screen, why don't you do, okay, this one. Okay, can you see the presentation?
Yes, we see it.
Okay, good. So thank you for this introduction, Radosav. So this is the work that was done mostly by Natalia Solchenska for her PhD work together with Andrea Gasparino and Lorenzo Castelli from University of Trieste, and I was helping on that, and I'm presenting today. So we'll go a little bit in the background here to explain what do we mean by the virtual center here, because there's a lot of talk about it and everybody has their own ideas, and depending on what you address, it might be slightly different, and go through the model we used, results, and the conclusions. So as we all know, the air navigation service provision has traditionally been set up to deliver the navigation services within the airspace of a state, and thus establishing national air navigation providers. The airspace of each state can be covered by one or more flight information regions where the en route air traffic is controlled by an area control center. And here you can see the upper region in Europe, courtesy of Eurocontrol charts. For example, you can see here that in Italy there are three ACCs in the upper airspace region. However, so this is the current architecture we have, that each state has its all the infrastructure that it needs for the provision of air navigation services. The physical layer with sensors and infrastructure, then the various ACCs that control the traffic within the state's airspace. A division of airspace architecture study is to go towards a slightly different version of the single European airspace system, to be based on modern technologies that could split the air traffic service provision from local infrastructure for data provision, thus enabling the coupling of service provision from geographical location, which could enable this virtualization, where service provider could use data from the common data services and practically controlling traffic anywhere. So that's the nice science fiction that we would like to explore, and how possible it is. So here we're focusing on this part only on the air traffic services, where we assume that this thing would be possible. Of course, this is a really big assumption because it assumes a lot of automation support to enable this virtualization that would then enable scalable capacity over the network. So the objective that we address here in this work is to understand the magnitude of possible benefits in terms of air traffic flow management delay reduction using the current ATC resources, meaning the how the airspace is designed right now, the number of sectors, the number of controllers, of course, in a very macro vision. The contribution here is a mathematical model that's designed to assess delay reduction that could be achieved by different virtual setups with current resources. And I'll explain what is the virtual center setup. Of course, it requires a fair number of assumptions. Some could be, I mean, at least in a current system, are quite science fiction. But this is something that the air traffic management master plan is aiming to achieve. So the virtual center here is a collaboration of a group of area control centers from 2 and above, which is enabled by virtualization in provision of location-independent ATC services. So here we assume that there is no need for physical consolidation of facilities, but it would require full technical and operational interoperability. And we assume the use of ATM data services from data providers. Another big assumption is that the ATCOs would have sector independent or licensing, or that they would be licensed on sectors of different ACCs. Here we are also exploring only ATC-C, which is capacity, and ATC-S, which is staffing regulation. So something similar as what Ramon was doing, although we do include staffing as well. So this is, again, I'm saying this is the macro analysis. So we pretty much, so these are the assumptions, and we don't take a lot of nitty-gritty details in this into account in this model. Sorry, I went a bit far. So to be able to to create this model, to formulate it, we needed to create several model-related assumptions. So an ACC has capacity issues when it generates the capacity and staffing regulations. Staff at an ACC-A can open a sector in ACC-B when the operational resources are lacking at the ACC-B. Then ACC-A can open an additional sector at ACC-B when it does not generate ATFM delay. So you can help only if you are not currently generating ATFM delay. and also that the number of currently open sectors is lower than those in planned opening schemes. So to explore this even further, we looked at, during our use cases, at 3 saturation levels, 0, 20, and 40% utilization of open sectors, where 0% just means that the sector was not open, but we also take into account the sectors that have very low utilization of the open sectors, just to explore, see what could be done with those things. Other assumptions that additional sectors at ACC-A can be controlled by ACC-B if the number of open sectors at ACC-A does not equal the maximum number of sectors. So if all the sectors are open, there's no place where another ACC can help. And we also, individual sector capacity is expressed as average sector capacity per ACC. So for each ACC, we calculated average sector capacity. So to be able to formulate the model, we need to introduce a few sets. The first one is the set of ACCs that we are looking at. So it can be, as I said, from 2, and it can go higher. Then the set of time intervals in the time period we are analyzing. So the time intervals are set to 1 hour, and the time period you'll see later is 2 months, more or less. Then we have a set of delay, DIT, which is a set of delays of ACCI at interval t. And then the set DJTI, which is ACCI's total delay that the ACCJ with whom the ACCI is collaborating can absorb at interval t. We have 2 sets of variables, XIJT, which is equals 1 if ACC's I and J collaborate at time t. And then DIJT, which is the minutes of delay, the ACCI of ACCI that can be absorbed by ACCJ at that time. So the objective of this model is to find the collaboration configuration at each time interval that minimizes the total delay, and is subject to the 4 sets of constraints which are very linked to those previous assumptions, which is at each time t, an ACC can collaborate with only one ACC, it cannot collaborate with itself. An ACC, if at any time ACC is requesting a collaboration with another ACC, it cannot then provide any delay transfer to other ACC. Delay is transferred from one ACC to another only if the 2 are collaborating, and the delay absorbed by an ACC is limited by either by the created delay of the ACC that has delay problems, or by the delay that the matched ACC can absorb. So just to show you this on an example, how this looks if you go and enumerate every single possibility. So this graph shows delay in DSNA for one summer day in 2019. Here we see with the red bars there were 2 ACCs in a French of the French provider that had delay issues. And the other 3 ACC had some underutilized capacity, like this one had 1 sector, 6 sectors, or 5 sectors. So if we enumerate all the possible combinations, we can see that, well, in this combination, these 2 sectors collaborating, and in these 2, and this is the reduction of delay that could be achieved, with the final delay then being that. So if we enumerate all and then go for the minimum, this would be the optimal collaboration that results with just 45 minutes of final delay from these collaborations. So to go now to the to our use cases that we checked with this model. So we used the data from 2 IRACs from Eurocontrol's DDR2 data that was kindly supplied by Eurocontrol to Natalia. So from there, we took sectors and their saturations, what were the delayed flights, the ATFM regulations, configurations in place, the opening schemes in place in those days, sector capacity. And then another set was the planned opening schemes that comes from the network operation plan, again, kindly provided by Eurocontrol. Scenarios that we looked at was to see what would be the delay reduction if we look at the different geographical extension of the virtual center. To begin with, we would go with a single NSP with a neighbor. functional airspace block, and single European sky. So, for example, for the single NSP, we looked at the DFS and DSNA, just because at that in that period they were the NSPs that had the highest delays, and they're also part of the functional airspace block of the FABEC. So that made the analysis a little bit easier. So we can see here what were the delay in minutes in the SES area, FABEC and DSNA and DFS in those two IRACs. So it's roughly 2 months. So it's 8 weeks of traffic. So with the example, so here we have the DSNA. So with the single NSP. So if we leave the DSNA to collaborate, so the ACCs within the DSNA collaborate with themselves, and we look at just opening the sectors that were planned but were not open, the reduction of delay could have been about 30%. But if we also included the helping through the sectors that have 20 or 40% utilization, the reduction could be much bigger. And on this, on the right hand graphic, we have what could be the delay reduction if the DSNA is collaborating with one of the neighboring ANSPs like MUAC, SkyGuide, and IADA, DFS, or ENAV. And here we can see that for each of the level of utilization saturation of the sectors, ENAV would be the best choice as a collaborator for DSNA. If you look at the DFS, here the situation is slightly different, because if the DFS would collaborate within itself, at least about half of the delay could be absorbed just internally. And here another interesting thing, and it probably also reflects the traffic density over certain parts of the network, that's in each of the different these saturation levels, it would be a different ANSP that would be the best collaborator. At the 0%, it would be SkyGuide. At 20%, it would be DSNA. And if we go at the 40%, then it would be the Czech NSP provider. If we look at the FABEC level, so we look at all of the NSPs that are part of the FABEC, if they would collaborate just within themselves, they would really just at the 0%, the reduction could be pretty significant. And even more if we go the utilization. And here is the different, like what would be the impact on the delay on the individual ANSP delay reduction in this case. And here, if you look at I think this is one of the funny, I don't know, for me, most interesting parts of the study is that if we include all of the NSPs that are in the single European sky area, the delay that could be, if they all collaborate, the delay could be reduced significantly. But if you look at it, if across the different utilization levels, it would be quite the same. 0, 20, and 40%. We get to the same amount of delay in the end, which in itself also indicates that there is, at least in the single European sky, in the complete network, we still have a fair amount of capacity, of unused capacity, that is floating around. Of course, it's not. It's easy to say that there is unused capacity. It's quite a different thing to actually use it. So to conclude, our results here show that virtualization could provide significant reduction of ATFM delay, and magnitude here again varies on geographical scope, which here is mostly showing also what is the traffic density over certain areas in the network. The results show that the current airspace organization and number of ATCOs available, they could provide ample capacity to deal with the majority of these capacities, so ATCC and ATCS regulations in the network. However, even though the virtualization could significantly reduce capacity issues, it could not on its own eliminate delays completely. So this indicates that, of course, a redesign of airspace with dynamic capacity sharing as proposed in the airspace architecture study or in other solutions that are being developed by the SESAR, might be necessary to overcome these current capacity-driven issues, and in addition to be able to accommodate more flights in the future. So we already mentioned we made a lot of assumptions to be able to do this. Well, not to be able to do this. We could have done this with none of these assumptions, but yeah. But this could be these results could be a good first approximation. So we mentioned we made a lot of assumptions, and the envisioned virtualization is in itself likely to entail reorganization of airspace, higher levels of automation, then change in ATCO training and licensing. So these are just some changes that would need to be in place. Of course, each of these changes is likely to significantly change the way of air traffic control and management at the micro level. And as always, the devil is in the detail. Is to be able to collaborate in even this simple way, a number of other matters, the simple way that we used in our model, which is just the two ACCs that are collaborating. A number of other matters should be resolved. To start with, ATCO training again, it should be extended or changed. And then another nitty-gritty example is solving sovereignty matters of allowing the control of states' airspace to be delegated to entities outside of state. We already have various cross-border cooperations in place today, so this issue can obviously be solved. It depends also how much time and the complexities of that putting in place. For the future work, this model should be extended, but to be able to introduce these different ATM solutions that I mentioned, the virtualization, ATCO licensing, and that, to be able to include this in the model and then to see what would that mean. And of course, for that to be a bit more useful, then it would be good to include the cost of this type of virtual center setup, so not to have a virtual center that the cost of which is extending too much. Okay, that's all for me.
Okay, thank you, Tanja, for the interesting presentation, for being on time as well. We already have a couple of questions in the Q&A. The first one I suggest we take from Paula Leal de Matos. Paula asks if it would be possible to also estimate benefits other than delay, for example, fuel efficiency, CO2 emissions, ATC productivity, and costs.
Would be possible other than delay. Yes, it would just need to be a different model. Not with this model. Yeah, we would need to think of how to formulate. But I think that there should be. I see fuel efficiency a bit more complex, just because it's a different data set. We would need to get data sets on the aircraft fuel efficiency and the emissions, but the ATC productivity and the cost, that's something that could be taken out of the data sets that we had. So yes, I think it would be possible to extend it and make a different model.
Okay, then there are a couple of remarks and questions from Sebastian Magnik. So the first one chronologically says, it's a pity that sector-independent ATCO licensing is assumed, because for a very long time ahead, this will either be not the case, or else in any case, an ATCO operating an unknown sector will offer less, probably much less capacity than a knowledgeable ATCO, even with the best automation support. This somehow relates to... Yeah.
I don't have anything else to add. I completely agree, but this is something like if we are thinking of going in that way, at least to estimate some of the possible benefits of the system. And as I said, again, the caveats are the devil is in the detail. If we really want that, then we need to know that this type of thing should be there. And I know it's, even if we go that way, it's going to take a long, long time to get there.
Okay, one more from Sebastian. He asks if he understands correctly that you assume a center not being in maximum capacity, that it has a spare capacity. For MUAC, at the times of little demand, there are also only a few ATCOs around, so often no chance to help out any neighbor. So this is concerning the assumptions of being able to share the capacity among.
Yeah, I think we were looking at the at the different times of day, it was a different possibility of getting it. Of course, you don't have the maximum open capacity all the day, especially not during the night, right? There is just a couple of centers, so we were looking at that, I think. I don't know the details, but I know, yeah, because we had this planned sector openings. So yeah, that's something that could be looked at further to see what it is. But yeah, that's true. If you have just 2 sectors that are open, you won't have more than controllers. Then would be to 2 or maybe 3 if they need to rotate.
Okay, and the last one for the time being is from Matthew Cormon or something. I'm sorry if you pronounce this wrongly. Good, helpful model. You partly answered this, but what one extra layer of complexity could be the next level of details that could be modeled? Would it be assuming different EDCO certification groupings, or would you see another priority?
So let me just check this question. Could be the next level that could be modeled. Would it be assuming different EDCO? I think at this point, since all of this is a bit of a science fiction, as long as we find a way of presenting this to be able to ingest it by the model, then we would go for that, for example. And it could be, for example, another extension would be just as maybe just going into more detail of just assuming the cross borders, like where you have like neighboring sectors that you could assume that they may be licensing and see what would be the impact of that. Like here, we really went into the assumption that everybody can control traffic anywhere, but maybe we can go for a more conservative assumption.
Gives you an upper bound at least. I mean,
exactly. Yeah.
This is something. Okay, and one more from the same attendee. The virtualization could be used to reduce delay or to reduce costs. Has the sensitivity analysis around finding a good trade-off between the two been looked at?
Not that I know of. I mean, the airspace architecture study looked a little bit into that. I have to say that I haven't looked at detailed analysis of simulation results that they did to perform that those simulations. And at least what's described in the airspace architecture study, it's also rather high level, but I haven't looked into that. Not that I know of that sensitivity analysis around this trade-off, particular trade-off has been done, or at least not for this type of scenarios.
Okie dokie. That's it for the time being, as far as I can see. No raised hands among participants, so I think we are done with this presentation too. Thank you, Tanja, for the presentation, for answering the questions, and to all other attendees once more. And please stay tuned for a couple more minutes just to see the final poster teaser, which will close this session. Thank you.
Okay, thank you.
I can't see or hear anything. I don't know about the others.
I can't seem to find the right one. Hold on 1 second.
Okay, that's it. Thank you, everybody, once again. Enjoy the break and see you around today and tomorrow in the rest of the conference. Thank you.
See ya.